Hello everyone. Till now, we have discussed single phase AC circuit. We know that our power system is three phase in nature. So, at all the conventional power plants, the electricity is generated at three phase. In this session, we are going to discuss how to generate three phase power, different types of voltage, current, relationship between voltage and current, and so on. Here, a schematic diagram of a three phase generator is shown. The generator consists of mainly two components or parts. First is a rotor and second is a stator. The rotor consists of a field winding, and this field winding is provided with variable excitation voltage. Whenever we provide a field current, that is direct current IF, this rotor will generate a magnetic field. The stator consists of three coils. These three coils are identical. They have same material, same number of turns, and all the three coils are connected at 120 degree apart from each other. That means the span between coil A and coil B is 120 degree. Coil B and coil C is 120 degree, and between coil C and A also 120 degree. This rotor is connected with a prime mover. Prime mover is nothing but, conventionally it is known as a turbine. It may be hydro turbine, steam turbine, or wind turbine. When turbine rotates, it will rotate the rotor, and as the rotor is having field winding on it, it will generate a magnetic flux which will be rotating in nature. When this rotating magnetic field is produced inside the stator, it will cut by the three windings. And as per Faraday's first law, whenever conductor or coil cuts the magnetic field, an EMF is induced in it. So as the rotor is rotating, the flux will be cut by all the three coils ABC, and in all the three coils, EMF or voltage is induced. Now, depending upon the maximum flux cut by each coil, the maximum induced EMF occurs at different instants. So this is called a three-phase power with three-phase voltage. The same diagram is shown with a different arrangement. In earlier case, the magnetic system or magnet was provided on rotor and it was rotating. In this case, the magnetic system is stationary. You can see these north and south poles. These are the magnetic poles. And these poles are stationary, whereas the coils are provided on rotor. So when the rotor is rotated, it will cut the magnetic flux and an EMF is induced in it. A point to note down here is all the three coils are placed at 120 degree from each other, same as earlier case. The difference is, in earlier case windings were stationary, here windings are rotating. So in both the cases, whenever we rotate the rotor, there will be a relative speed, relative velocity between a magnetic field as well as coil, and as per the Faraday's first law, an EMF is induced in all the three coils. The same diagram is shown with waveforms, where on the right hand side diagram you can see there is a three-phase supply which is generated when we rotate the rotor. The notations are RYB, that is red, yellow and blue, and these three colors are for three coil induced EMF. So coil A induced EMF is noted by red waveform, B with yellow waveform and C with blue waveform. We can note down here that the maximum or peak value in all the three coils are same because all the three coils are identical, but the instant at which the maximum voltage occurs is different in all the three coils. For example, in coil A, the maximum voltage occurs here. In coil B, maximum voltage occurs after 120 degree coil A, and in coil C, the maximum voltage occurs or induced after 120 degree than coil B. So we can say that in these three coils, the induced EMF has 120 degree phase shift with respect to each other. So coil B induced EMF lags behind coil A by 120 degree, coil C lags behind by 120 degree with coil B, and so on. So this is how we can generate the three-phase voltage or three-phase current using the three-phase generator. In this animation, you can see when the rotor is rotated, the EMF is induced in all the three coils. Here phases are shown by A, B and C. Depending upon the position of the magnet, the maximum induced EMF occurs, that we can see in the waveform. The moment when the rate of change of flux linkage is maximum with any coil, in that coil maximum EMF is induced. So as per the arrangement, first the maximum EMF induced in blue phase or phase A, then after 120 degree the maximum EMF induced in red coil or coil B, and after 120 degree in coil C or green coil the maximum induced EMF occurs. Similarly, the instantaneous values of all the three phase induced EMF also depend on position of the rotor. When rotor is rotated, the magnetic flux will be cut, and depending upon the amount of magnetic flux cut by these three coils, their EMF or instantaneous value of EMF is decided. Now this type of generator is available mostly in all the thermal and hydropower plants, where the magnetic system is rotated or magnetic system or field system is provided on rotor, whereas the coils are provided on stator. The same diagram is shown with a little bit more animated view. Here also magnetic field is rotated and there are three coils, phase 1, 2 and 3, or coil 1, 2 and 3, and depending upon the position of the magnet, their maximum value is individually shown in first three waveform, and if we combine all the three waveform, we will be having the last three phase voltage. As I said earlier, the three coils are placed at 120 degree from each other. So the phase difference between these three voltages remains 120 degree constant throughout the period. Now if we draw the waveform, then the three phase voltage or current waveforms will be like this. Here we have taken voltage. So for x-axis we consider the time or omega t or theta, position of the rotor, and on positive y-axis it is plus v, on negative y-axis it is minus v, and depending upon the rotation the three phase waveforms will be available like this. So you can see here coil A becomes maximum, induced EMF in coil A becomes maximum at 90 degree. Coil B induced EMF started at 120 degree. So this is 120 degree instant. Coil A EMF started from 0, coil B started from 120 degree. So there is a phase difference of 120 degree between B and A. Similarly, coil C induced EMF started at 270 degree. So there is a difference 240 degree, sorry, this is 240 degree. So there is a difference of 120 degree between induced EMF of B and C. So here coil B induced EMF lags behind A, coil C lags behind B, and so on. Let's draw one more waveform. So the same information is shown here with color notation RYB. Here also the phase difference is 120 degree and the maximum induced EMF occurs at 90 degree in phase A, after 120 degree in phase B, and after 120 degree in phase C, and so on. In this case, the V1, V2 and V3, these three are in three instantaneous voltages, and three instantaneous voltages are shown with the help of three different colors. So the same waveform or diagram, you just go through the presentation I have said. Induced EMF in all three phases. The important point to note down is in all these waveforms, the maximum value in all the three phases remain same because coils are identical. Now, if we start with the first waveform and write the equation of instantaneous voltage or instantaneous EMF, then EA is the instantaneous EMF in coil A. And as it is started from 0, we can write EA is equal to EM sine omega t. Just recall the single phase circuit. Then coil B is having 120 degree phase shift. Coil B induced EMF lags behind coil A by 120 degree. So the instantaneous value becomes EB is equal to EM sine omega t minus 120 degree. Similarly, phase C induced EMF started after 120 degree of phase B. So EC is equal to EM sine omega t minus 120 minus 120. So total it becomes EC is equal to EM sine omega t minus 240 degree. So the induced EMF in coil C started after 240 degree compared to phase A. So we have three equations. Equation 1 EM sine omega t, equation 2 EM sine omega t minus 120 degree, and EC EM sine omega t minus 240 degree. Then out of these three instantaneous values EA, EB and EC, if we calculate the resultant instantaneous EMF, resultant value of all the three instantaneous induced EMFs, then it is summation of EA plus EB plus EC. Now this is instantaneous values EA, EB, EC. So let's put three equations for EA, EB, EC. EA is equal to EM sine omega t, EB is equal to EM sine omega t minus 120 degree, and EC is equal to EM sine omega t minus 240 degree. With little bit mathematical simplification, we can have this is equal to EM sine omega t plus 2 sine omega t minus 180 degree into cos 60 degree. This is nothing but EM sine omega t minus 2 sine omega t cos 60. And if you calculate for one cycle, its value is 0. This value becomes 0 because if you put cos 60 value, then it becomes sin omega t minus sin omega t, and sin omega t minus sin omega t is 0. 0 multiplied by EM, it is 0. That means the resultant of three instantaneous EMF or current is always 0 at any instant. If you take any instant, at that instant the resultant value of three instantaneous values of current or voltage is 0 in perfectly balanced three-phase supply system. The same thing is represented with the help of vector or phasor diagram. So you can see here E is equal to EM sin omega t. So EA vector is considered as a reference. After 120 degree, that is minus 120, so we have EB, and after EB 120 degree there is EC. So you can see between three vectors, there is a phase difference of 120 degree. And if you do the resultant, if you calculate the resultant of these three vectors, it will be 0. For example, first if we calculate resultant of EA and EB, so the resultant of EA and EB will be this value ER. ER vector is exactly equal in magnitude and opposite to EC. So they will cancel out each other and we will have a 0 resultant value. So this is mathematical proof and this is a graphical proof. Now phase sequence. The meaning of phase sequence is the order in which the three phases or three coils attain their peak, maximum or crest value. For example, there are three coils ABC. In which manner they attain the maximum value? If first coil A attains the maximum value, after 120 degree coil B and after 120 degree coil C, then the phase sequence is called ABC. But if coil B attains maximum value first, then coil A and then coil C, then the phase sequence is called BAC. So phase sequence is the manner in which the coil attains the maximum value when they generate the power or voltage. So here you can see, first let's say this is the starting point. First coil 1 attains the maximum value when we proceed in this direction, positive x-axis direction. Then coil B or coil 2 achieves the maximum value and then coil 3 achieves the maximum value, and this is repeated. So the phase sequence for this waveform is 1 2 3. So 1 2 3 1 2 3 1 2 3 and so on. In this case, the blue waveform achieves the maximum value first in positive direction, right? Then coil 2 achieves the maximum value and coil 1 at the end or at the last. So in this case, the phase sequence is 3 2 1. In earlier case it was 1 2 3. Here it is 3 2 1. This phase sequence is also known as a phase order. Order means sequence in which it is becoming a maximum. We can change, we can reverse the phase sequence just by reversing the rotation of magnetic field. For example, in this case, if the rotor, let's say this is a generator, and if we rotate this rotor with ns pole in clockwise direction, in that case if the phase sequence is 1 2 3, if we rotate the rotor in anti-clockwise direction, the phase sequence will be reversed. It will be in opposite manner. Now every time we don't need a three-phase generator to generate the three-phase power. We can also generate the three-phase power with the help of three individual single-phase generators. So here there are three different generators. This is generator 1, let's say generator 1, generator 2 and generator 3. These three are single-phase generators, and if they are individually operated, then they will generate single-phase supply. We can have a three-phase supply by connecting these three generators in an appropriate manner, and this appropriate manner is either star connection or delta connection that we discussed in first chapter, that is DC circuit. You can see here every coil of the generator is having two ends, the starting end and finishing end. Here starting, finishing, starting, finishing. We can connect these three generators in either star or delta so that we can have three-phase power. So this is an alternate method to generate three-phase power with the help of three single-phase generators. Now here, if we operate these three generators individually, then the important disadvantage is we will need 6 conductors. You can see there are total 6 number of conductors in all the three machines, three generators. But if we connect this in appropriate manner, we can reduce the number of conductors. So here the three phase are generally interconnected. The three individual generators or coils, they are interconnected, which results in substantial saving of copper. So out of 6 conductors, we can reduce the conductor to 3 or 4, and as a result there will be saving in copper material. The general methods of interconnections are, as I said, star connection or Y connection, and mesh connection or delta connection, or sometimes it is also referred to as D connection. So let's see what is star connection and what is delta connection, which are popularly known. First, star connection. Star connection is the connection in which the similar ends of all the three generators, they are connected together. For example, starting ends of three coils. It could be finishing end also, but either starting end or finishing ends, they are connected together, and that point of connection or common point is known as N. N stands for neutral. So the same thing we have discussed in chapter 1, that is star connection of three resistors is when we connect all the three similar ends together. It will create a common point which is known as the neutral. The neutral point is also known as either a star point. So you can say either neutral point or star point as the connection is star itself. So in the diagram A, you can see three phases. They are connected in star. So S stands for starting, F stands for finishing. So all the starting points are connected together here, and this is our neutral point or star point. This neutral point or star point, now instead of having three conductors, we can put only one conductor. So there will be a saving of two conductors or materials of two conductors. So the same diagram is shown here. This is the generator, three generators connected in star, and at these terminals we can connect three-phase load. So after eliminating two redundant conductors, we will have a final diagram shown in B. So you can see here now in the phase R, current flowing is IR, phase B, current flowing is IB, and phase C, current flowing is IY. So IR, IY, IB are three currents, and the three currents are induced in these three coils. There is only one neutral conductor, and the voltage between, let's say, terminal, this is terminal R, this is terminal B, and this is terminal Y, and this is terminal B. So the potential or induced EMF in coil R is the potential between terminal R and terminal N. So it is denoted by ER. Similarly, the induced EMF in Y phase is the potential difference between terminal Y and terminal N, which is written as EY. And the potential or induced EMF in coil B is EB. In these three outer conductors, the current IR, IB and IY are flowing, and here we can connect three-phase load. Now this three-phase load could be any, can be three-phase induction motor or any three-phase load. It can be society or college or hotel or anything. So this is how three single generators are connected with each other in a star manner to generate three-phase supply. The three conductors meeting at point N are replaced by a single conductor, as I said earlier, and that is popularly called the neutral conductor. This type of system is known as three-phase four-wire system. So the star connected network, star connected system, star connected generator which is having a neutral conductor is popularly known as three-phase four-wire system. So this is three-phase four-wire system. Three-phase four-wire system because there are three phases R, Y, B, and four wires because there are total number of four conductors, three phase conductors and one neutral conductor. So the star system is always three phase four wire system. Then in this type of connection, the vector sum of three currents IR, IY and IB, the vector sum is always 0. This we have already proved that the vector sum of instantaneous induced EMF or voltage is always 0. The rule is also applied for current. So whether it is voltage or current, their vector sum at any instant will be 0. The potential difference between any terminal or line and neutral point gives the phase or star voltage. So this is important. In this diagram there are two types of voltages. One voltage is called a phase voltage and another voltage is called a line voltage. So the phase voltage is the voltage between any phase and neutral point. So in our earlier diagram, if you recall, then ER, EY and EB, these three are the voltages between phase and neutral respectively. So these three voltages are called phase voltages. But if we measure the voltage between terminal R and terminal Y, terminal Y and terminal B, and terminal B and terminal R, then this type of voltage is called a line voltage. So the phase voltage is induced EMF in individual coil which is measured between phase conductor and neutral, and line voltage is the voltage which is measured between two phases, and that's why it is also known as line to line voltage. Simply it is called line. Now let's see what is the relationship between voltages and currents in star connection. Here the meaning of voltages and currents is phase voltage, phase voltage, line voltage, phase current, line current. So what is the relation? The voltage induced in each winding, as I said, it is called phase voltage, and current induced in each winding likewise called a phase current. So in the diagram, left hand diagram, you can see this ER, EY and EB. These three are phase voltages, and VRY, that is voltage between phase R and phase Y, is line voltage. Similarly, VBR, it is the voltage between phase B and R, and VYB is the voltage between Y and B. We can draw the vector diagram. So ER is taken along the x-axis. After 120 degree there is EY. So this is 120 degree. After 120 degree there is EB. So ER, EY, EB are three phase voltages. In these three coils, the induced current are, let's say IR, here it is IY, and here it is IB. So three induced currents or phase currents are IR, IY, IB. So if you take the case of R phase, then in the R phase there are two phase quantities, ER and IR. And what is the relation between this ER and IR? This is inductive circuit or inductive component, inductive coil. And we know that in inductive coil, the current lags behind voltage. If it is pure inductor, it lags behind voltage by 90 degree, exactly 90 degree. But as we know, we have discussed number of times that pure inductor is like honest politician. It is not possible to have a pure inductor. So the phase current IR lags behind ER by some degree phi, and this phi degree is always less than 90 degree. So you can see in the diagram, that IR lags behind ER by phi. Similarly, IY lags behind EY by phi degree, and IB lags behind EB by phi degree. So this is the vector diagram of phase voltage and currents. Now we would like to calculate line currents and line voltages. So how can we get the line voltages and line currents? Simply, the line voltage VRY is nothing but it is the voltage between line 1 and line 2. That means phase R and phase Y. So what is the magnitude? What is the value of VRY? VRY is nothing but induced EMF in phase R plus induced EMF in phase Y. Now please remember, this is vector sum. So VRY, we can write here VRY is equal to ER plus EY. Similarly, what is VBR? VBR is EB plus ER, and similarly VYB is EY plus EB. So if we do the vector sum of all the pairs of voltages across two terminals or pairs, then we will get a line voltage. So let's see how can we do. In this diagram, every type of voltage and currents are shown. So ER, IR, the notations are different. ENR, INR are used. But one thing we can observe from this diagram, that induced current is INR in phase R. So this INR is known as the phase current. This current is known as phase current. Now the same phase current is flowing in this direction, and when it comes in outer conductor at this terminal, current IR is available. So this current IR is known as line current. You can see in all the remaining phases same thing, that induced EMF in phase Y is ENY. So this is phase voltage, and induced current in the same phase is INY. So this is phase current. The same phase current flows through outer conductor, and when it flows through outer conductor, it becomes IY. In phase B, induced current is INB. When it reaches into outer conductor, it becomes IB. So what is the conclusion? If it is a star connected network, then in star connected network, the phase current is equal to line current. So we can write I phase is equal to IL in short. So what is the relation of phase current and line current in three-phase star connected system? The relation is phase current is equal to line current. This is very easy. Now let's see the relationship between voltages, that is phase voltage and line. So in a perfectly balanced system, that ER, EY, EB are same because all the three coils are identical and they are rotated or they will cut the same amount of maximum flux. ER, EY, EB are same and we label it as E phase, that is phase voltage. Now already we have discussed VRY is nothing but vector sum or vector difference of ER and EY. If you see that vector diagram, it will be vector difference. VYB is equal to EY minus EB and VBR is equal to, or we can write EB plus ER, EY plus EB and ER plus EY. So the same thing is written here in mathematical form. Now let's calculate VRY first. This is the line voltage. Remember, line voltage between phase R and Y by compounding ER and EY reversed. So if you recall what we have written, VRY is equal to ER minus EY. So minus EY is nothing but EY reversed. So let's draw the vector diagram first. Okay, so here you can see this is ER and this is EY. So let me draw here. This is ER, this is EY. What we need to do? ER minus EY. So this is ER and minus EY will be in this direction, 180 degree in opposite direction. This is minus EY. And if we add ER and EY, we will have a vector sum VRY. So this is VRY. So here you can see ER minus EY and this is VRY. Similarly, EY and minus EB. So this is EY and this is minus EB. We will get VYB. In the same manner, EB minus ER. So this is positive ER, this is minus ER. So EB minus ER, we will get VBR. So we have three line voltages, VRY, VYB and VBR. Now this three line voltages are same in magnitude. You can see all the three vectors VRY, VYB and VBR are same in magnitude. Also, if you see one more thing, one more important thing, then the angle between VRY is line voltage. So this is line voltage and this is the phase voltage. So the angle between line voltage and phase voltage is 30 degree. And this relation is true in all the remaining line voltages case. So the total angle between ER and EY is 60 degree here. ER and minus EY actually. This is the total is 60 and this is 30 degree. So using mathematical step, we can calculate the magnitude of VRY vector. So VRY is 2 into E phase. E phase is ER. So 2 into E phase into cos total angle divided by 2. So 2 into E phase, this is cos 30, put the value of cos 30 root 3 by 2 and we will get 2 to cancel. So we will get root 3 E phase. So what is VRY? This is line voltage is equal to root 3 times phase voltage. And the same relation is true for remaining two line voltages, that is VYB and VBR. In general, we can write that VRY is equal to VYB is equal to VBR is equal to line voltage. Let's say we give the name VL, and hence in star connected network, the line voltage is equal to root 3 times phase voltage. Line voltage is root 3 times phase voltage. So from the diagram, from the vector diagram, it should be noted that all the three voltages are also apart from each other by 120 degrees, same as phase voltages. Line voltages are 30 degree ahead of their respective phase voltages. So if you recall, this was our ER and this was our VRY, and this degree is 30 degree. So line voltage is ahead by 30 degree with respect to phase voltage. The angle between line current and corresponding line voltage. So here there is line current. This angle is phi. So the angle, this is IR, right? So the angle between line current and phase current is 30 plus phi. 30 plus phi. With current is lagging behind line voltage. This already we have discussed, so I am not repeating. The relation of line currents and phase current is line current is equal to phase current, that is IL is equal to I phase. We can calculate the power for three-phase star connected network. So the total active or real or true power is the summation of three-phase powers generated by three individual coils. Hence, the total active power is 3 multiplied by single phase power. So 3 multiplied by phase power. So P is equal to 3. What is phase power? Phase power is V phase I phase into cos phi. This is the equation of active power, Vi cos phi. So 3 into V phase I phase cos phi. Let's put the value in terms of line quantity. So V phase is equal to VL upon root 3. We know that VL is equal to root 3 V phase. So V phase is equal to VL upon root 3. And IL is equal to I phase. So let's put these two value, root VL upon root 3 and IL. In place of I phase and V phase, we will get P is equal to 3 VL upon root 3 into IL. So this root 3 upon root 3, we will get P is equal to root 3 VL IL cos phi. This is in watt. So we get the power, the value of power in three-phase star connected network is P is equal to root 3 VL IL cos phi. So this is three-phase star connected network. Now the phi is angle between phase voltage and phase current. Please remember, phi is not the angle between line voltage and line current, but phase voltage and phase current. The angle between line voltage and line current is 30 plus phi. Similarly, the total reactive power is given by Q is equal to root 3 VLIL sin phi. So active power P is root 3 VLIL cos phi. Q is equal to root 3 VLIL sin phi. Its unit is VAR, volt ampere reactive. By convention, if the reactive power of a coil or inductor is taken as positive and that of a capacitor is negative. So if it is inductive circuit, Q is taken as positive, and if it is a capacitive circuit, then we know that the phi is negative, so it becomes minus root 3 VLIL sin phi, and the total apparent power or complex power is given by S is equal to root 3 VLIL, or S in the case of P plus JQ, complex power. The magnitude is S is equal to under root P square plus Q square, and the unit is volt ampere, VA. In the next lecture, we will discuss delta connection or mesh connection or D connection. If you have any query, you can ask me through my WhatsApp. Thank you. See you in the next lecture.